So as we jump into our Module 13.2, our second section for Module 13, we're finishing up our chapter dealing with columns, specifically looking at our load design. So within this module, we're going to take a look at centric loads and eccentric loads and how they're related to design. So within this, we're going to take a look at the theory for these above topics, talk about some of the key equations, look at some practical applications, and then go through my hand solutions to a couple different problems. So as we begin this module, we're first going to take a look at the topic of our centric load design. Now previously, we determined critical loads of a column by using Euler's formula, and we determined the deformations and stresses in eccentric loaded columns by using the secant formula. Now in each case, all stresses remained below our proportional limit, and the column was initially a straight homogeneous prism. Now, in reality, real columns are going to fall much short of this idealization. So to account for the differences between a real column and an idealized column, the design is normally going to be based on empirical formulas that are developed from laboratory tests. So as we just stated, the previous analysis assumed that these stresses fell below that proportional limit and are initially straight and homogeneous columns, which is not always the case in reality. So we had to go back and reference this to some experimental data that we did in the labs. So from this, what we have over here now is a plot of this test data, this experimental data for steel columns. So we can see our ratio over here from our effective length over our R on our x-axis, and we have our critical stress on our y-axis. Now we can see with this curve here, if we stay over here on the left-hand side for our short columns, we can see our yield strength is much higher on our critical stress axis over here for the short columns. But now as these columns get longer, our slenderness ratio, our effective slenderness ratio, increases over here with our LE over R as they get longer. And with that, as these get longer, we can see that our critical stress gets lower as we follow down on this curve here. And we have an equation here for our critical stress that we've seen before, that our sigma sub CR is equal to our pi squared E, which are modular elasticity for that material, all over that ratio over LE over R for our effective length over R quantity squared. So now if we're looking at these large ratio here for our LE over R, so as we get out here towards our longer columns here for that ratio of our effective length over R, for that effective slenderness ratio here, we see that our critical stress follows Euler's formula and depends upon our modulus of elasticity, E here, but not upon our sigma sub Y or our yield strength. So we can see that in this equation that we have over here with our graph. Whereas contradictory to that, for our small LE over R ratio, so we're coming over here on our short columns over here, we can see that our critical stress is approximately equal to that sigma sub Y or our yield strength right here. So for these small columns, this is pretty close to that value right there. Now for the intermediate case right here, for our intermediate columns, we can see now we have that same ratio, our LE over R, effective length over R. We can see that our critical stress here is going to depend upon both of those, our yield strength and our modulus of elasticity. So now as we continue on with our discussion of the centric load design, let's take a look at the specific example of structural steel. And for this, we're going to reference back to our American Institute of Steel Construction. As we can see in our graph down below, we have the design curve for column buckling recommended by the American Institute of Steel Construction. So we can see on our x-axis, we have our L over R, which we recall this is our slenderness ratio. And on our y-axis, we have our sigma sub CR, or our critical stress. So this curve is going to represent the variation in our critical stress as a function of our slenderness ratio. Now, another thing that we want to note here is that this curve does not incorporate any factor of safety. And if we look at this section here, from A to B on our curve, we can relate this back to our equation 10.38 in our textbook. So as we can see in our graph, if we're going from A to B, this is going from 0 up to a value here of 4.71 times the square root of E, our modulus of elasticity, over our sigma sub Y. So that is the range that we're in when we're going from A to B. So that's where we have this, if our slenderness ratio is less than what it is here at B, that 4.71 times the square root of our E over our sigma sub Y, then to find our critical stress, our sigma sub CR, we can use that relationship from equation 10.38, where we see this as 0.685 to the exponent of our sigma y all over our sigma e, where our sigma e is given to us in our equation 10.39 in our textbook as this ratio here of pi squared times our modulus of elasticity, all divided by that slenderness ratio, our L over R quantity squared. Now, what if we have the case where our slenderness ratio, or L over R, is equal to 0? Well, that's going to put us right here at our origin. And this is going to be right on our y-axis. In that case here, we can see that our sigma sub CR is going to be equal to our sigma sub y. So our critical stress is equal to our yield strength for the case where our slenderness ratio, L over R, is equal to 0. We can also look at what is the case when our slenderness ratio, or L over R, is right at B. So this is where this would be equal to, our L over R is equal to this relationship here of 4.71 times the square root of our modular elasticity over our yield strength, our sigma sub y. And that's the case where we relate this back to our equation 10.41 in our textbook. So now that we've looked at our slenderness ratio, our L over R, from A to B, at A and at B, now we want to take a look at it from B to C. So this is the case where we're going to look at our equation 10.40 in our textbook. And this says that our slenderness ratio, our L over R, is going to be greater than our value here at B. So it's going from B to C. So it's going to be greater than that value at B of our 4.71 times the square root of our modular elasticity all over our sigma sub y. In that case, our critical stress is going to be given by the relationship that our sigma sub CR is equal to 0.877 times our sigma sub E, which our sigma sub E goes back to that relationship that we saw in our equation 10.39, where sigma sub E is equal to pi squared times the modular elasticity all over our slenderness ratio, L over R, quantity squared. So as we mentioned earlier, this curve does not take into account any factor of safety. So factor of safety must be used in the final design according to our AISC. So what we can do is we can reference back to our equation 10.42 in our textbook and show that our allowable stress is equal to our critical stress divided by our factor of safety, where in this case here, for our example, our factor of safety will be 1.67. So we can plug that in order to calculate our allowable stress, or compare it for our final design using our value from our critical stress. So now that we've had the opportunity to look at our centric load design for structural steel, let's take a look now for the same centric load design but for aluminum. And we'll reference back to our Aluminum Association Incorporated for this graph that we see here. So we have a design curve for columns recommended by the Aluminum Association, and we can see on our x-axis we have our slenderness ratio, and now on our y-axis what we have here is our allowable stress, or sigma sub ALL. So with this here, let's take a look at two different types of aluminum. So the first aluminum we're going to take a look at is our aluminum 6061 T6. Then we'll also take a look at our aluminum 2014 T6. And we'll go through an example actually with this aluminum 2014 T6 utilizing some of these relationships. So let's take the example if we're dealing with our aluminum 6061 T6. For this material, if our slenderness ratio, our L over R, is going to be less than our 66, then we have a relationship shown here for our allowable stress. Our allowable stress in two different units, either in KSI or MPa, are given to us. Now, if we're dealing with units of KSI, and again, pay attention to the problem you're working at, look at your units and make sure you're in the correct units. If you're dealing with KSI, then we have this relationship that our sigma allowable, or allowable stress, is equal to 20.3 minus 0.127 times our slenderness ratio of L over R. And that's in units of KSI. Now, if we're dealing with units of MPa, then it's going to be the same thing down here, but converted to those units that our allowable stress is equal to 140 now, minus 0.874 times that slenderness ratio, or L over R, in units of MPa. Now, that was for the case of our slenderness ratio being less than 66. What if our slenderness ratio is greater than 66? Well, then we have the relationship here that our allowable stress is equal to, in units of KSI, 51,400 KSI all over our slenderness ratio, L over R squared, or in MPa, that would be 354 times 10 to the third MPa all over that slenderness ratio, L over R squared. Now, this is an assumption we're going to have to make for a lot of problems of whether our slenderness ratio is going to be less than or greater than these values. For this case here, aluminum 6061 T6. If we're going to be less than 66, we can go through with this assumption, use this relationship here. Then in the end, we're going to need to do a double check. And if we were wrong, we may have to go with the other case and use this other relationship. And as I go through an example problem, I'll show you a case of where we made the right assumption and where we made the wrong assumption and how we can utilize that. So now let's take a look at our other material, our alloy 2014 T6. So for this one here, slightly different. If we're looking at our slenderness ratio, our L over R, if this is going to be less than 55, then our allowable stress is given to us as the relationship shown here for both KSI and MPa, depending on which units we're using in. So if we're in KSI, it's going to be 30.9 minus 0.229 times that slenderness ratio. And for an MPa, it's 213 minus 1.577 times that slenderness ratio, L over R. Now, if this is going to be greater than or equal to our 55, then we have the case down here that our sigma allowable is going to be equal to our 55,400 KSI, so units of KSI, all over L over R slenderness ratio squared, or for an MPa, it'd be 382 times 10 to the third divided by our slenderness ratio, L over R squared. So these relationships for our slenderness ratio and our allowable stress for our aluminum are shown in our textbook in equations 10.43 through equation 10.48. We can see this is for our alloy 6061 T6 and for our alloy 2014 T6. So now what I would like to do is apply some of that theory and governing equations to an example problem. So let's take a look at our sample problem 10.4. Within this problem here, they tell us that we have an aluminum alloy, so now we're going to use that 2014 T6. And with that, they want us to determine the smallest diameter rod, so we can see this is our diameter of our rod D right here, which can be used to support a centric load. So we're dealing with a centric load here where P is equal to 60 kilonewtons. So we can see that in our diagram off to the left. There's our P is equal to 60 kilonewtons. It's a centric load right in the center. They tell us there's two different cases that they want us to determine this diameter D for. It's for an L value here of 750 millimeters and an L value, a length here of 300 millimeters. So pay attention to our units. This is in kilonewtons. This is in millimeters. These don't agree, so make sure we do the correct conversions. So as we begin this problem, we've read through our problem statement, we've taken a look at our given diagram, so what do we want to do next as we're solving this problem out by hand? Well, the first thing we want to do is create our setup page, and on that setup page, we're going to have our given information, what they've asked us to solve for, any diagrams we need, and any assumptions as well that we're going to be making. From there, what we're going to do is we're going to come up with a procedure for analysis, look at our governing equations that apply for the specific problem, go through step by step through that procedure for analysis for our solution, and then do any checks that we need to along the way. So before I begin my setup page, I kind of read through that problem statement. In my head, I come up with a procedure for analysis. Okay, I know this, I don't know that. What am I thinking for procedure for analysis? So that's what I've done here is my solution procedure. So with this, I'm looking at it and saying, okay, the diameter is unknown. And the slenderness ratio cannot be evaluated without that known diameter, so therefore we're going to need to make an assumption on what the slenderness ratio is going to be and what regime we're going to utilize from those charts and those governing equations that we saw earlier. And we know now our material type, so I know I can reference back to that. I've seen this earlier in the module. I'm going to make that assumption and utilize that and do a double check. From there, I'm going to calculate the required diameter for that assumed slenderness ratio regime. And after that, I'm going to evaluate that slenderness ratio and verify if our initial assumption was correct. And if it's not, repeat this process as necessary with a different assumption. So this is my general idea for my procedure for analysis as I go through the solution to this problem. So our first step as we begin our solution to this problem is to create our setup page. So this is our sample problem, 10.4. I write the name of the problem there. Up in the top right, you'd have your name, when the due date is, what assignment it is up here as well. Then we begin with our given information. So from our problem statement and our initial given diagram, we know this is an aluminum alloy, 2014 T6. We know it's a circular rod, and we know it's going to be a centric load. Now, what do they give us for our given information? Again, we want those four different things. We want the variable name, we want the value, the numerical value, we want the units, and how then the fourth thing is how it relates to our problem. So this is P, our load. Has a value of 60 in units of kilonewtons. So P is equal to 60 kilonewtons for our load. Now, for part A and for part B, they give us a different L, which is our length. And for part A, this is 750 in units of millimeters. We can do that conversion. It's 0.75 meters. For part B, our L, our length, is equal to 0.3 meters or 300 millimeters. I write it out both ways. I'm not quite sure where I want to use and how I want to use it, but to have it already converted on my setup page, it makes it easy for me to quickly switch back and I don't make a mistake and put a decimal in a wrong spot as I'm going through the solution later on. I also know that D is my diameter, and that's what I'm going to be looking for. So that brings us down to our find, what they're asking us to solve for. They want us to find the smallest diameter D that can be used to support the centric load. So we know it's a centric load again. And this is our value of P for our centric load there, P, of 60 kilonewtons that's given to us in the problem statement that we can see right there. So if, for part A, L is equal to 750 millimeters, or 0.075 meters, and B, if L is equal to 300 millimeters, or 0.3 meters. So now I've taken all the information from my problem statement, initial given diagram, created my setup page with all my givens, variable names, numerical values, units, how it relates to my problem, everything they've asked me to solve for, and I've even redrawn my diagram as well, and I left this all in terms of variables, P, L, and D, and these are my point A and point B there, and I've shown that this is a centric load as well. So now that we've had the opportunity to read through our problem statement, initial diagram, and now create that setup page, we can reference back to that setup page at any point and utilize that information, all of the givens, all of the information they're asking us to solve for, any of the unit analysis and conversion we've done, we can quickly reference back to that and plug it in as we're going through our procedure for analysis towards our solution. So now let's begin our solution. We'll take a look at our procedure for analysis. What are the steps along the way? Well, we're going to utilize our allowable stress equations. And with that, we're going to take a look at our slenderness ratio, our L over R, and make an assumption. Now, based upon that assumption, we're going to go ahead and calculate the diameter based on that slenderness ratio assumption. And from there, we'll evaluate that assumption, decide if it's correct or not. If it is correct, we're all set, and that diameter is our answer. If the assumption is shown to be incorrect, we'll need to go back through, make another assumption, and repeat these steps to calculate the diameter based upon the new assumption. So as we're beginning our solution, going through this procedure of analysis, the first step we want to do is take a look at the cross section for this solid circular rod. So for a solid circular rod, we take a look at the top view of this right here, and we can see we have a circle with a radius. We're calling this radius our C. So this is something that's important to pay attention to, is our variable names. So for this case here, our C is going to be the cylinder radius and not R. R is going to be, in this case, our radius of gyration. Now we can relate that back to C, which is what we're going to do right here, but we need to realize that C is the radius of this and not R. R is that radius of gyration. Now our equation for radius of gyration is given to us as a square root of our I over A. Well, for a solid circular rod, what is our equation for I? Well, I is going to be pi over 4 times that C, which is our radius here of the circle, to the 4th. And what is our A? For the denominator within this, our A is going to be that area, which is our pi, times our C, which is the radius of this here, squared. So we can plug this value, this relationship for I, into our numerator, and we can plug this relationship for A into our denominator there. We end up with this that we see here, and I've written it out by hand over here, that our R, our radius of gyration, is equal to the square root of pi over 4 times C to the 4th divided by pi times C squared. So we can cancel things down, reduce this, and we end up with a relationship between our radius of gyration and our radius of our sphere is that R is equal to C over 2. And that's something that's going to be important that we pay attention to and we make sure we plug in the correct value as we're going through our solution moving forward. So now we can reference back to our problem statement or back to our setup page as well and realize that there's two parts of this problem. So let's solve these each individually. Let's deal with part A first. In part A, they give us a value for that length L. L is equal to 750 millimeters, or with our unit conversion, this is 0.75 meters. Now what are we looking to do? We're looking to determine the diameter of the rod, a value for D. So with this, from our procedure for analysis, we're going to take a look at our slenderness ratio, and we're going to make an assumption. So L over R, that slenderness ratio must be assumed. So let's make the assumption that our slenderness ratio, our value for L over R, is going to be 52.7. And this comes from those tables we saw earlier in the module, those relationships, those equations. So we can use our equation 10.48b for the material that we're utilizing here that was given in the problem statement and our value for that slenderness ratio, L over R. So this comes from page 726 in our textbook, where L over R being greater than or equal to that 52.7, we have the following relationship here for our allowable stress. Our allowable stress is equal to, and if again, pay attention, are we in KSI or are we in MPa? So for our case here, we're in MPa, so this is 356 times 10 to the 3rd MPa, all over our slenderness ratio, L over R squared. So for a centric load, we can now also recall, that's given to us our problem statement, it's a centric load, that we have our allowable stress is equal to our load over our cross-sectional area. So now we can say that this sigma allowable here is equal to this relationship up here, set those two equal to each other, and we see now that 356 times 10 to the 3rd MPa divided by our slenderness ratio, or L over R squared, is equal to, from this relationship here for a centric load, our P over A. So now we look at this, we don't have a value for L, R, P or A, but these are all dependent on each other, and some of this is given information. So now we can go back to our setup page and go back to our relationship between our C and our R, and go back up to our problem statement here for our value for L, and plug all this information in to this equation here. So where did this come from? Where did that relationship come from for our assumption? This is back to our textbook. So we're dealing with our aluminum 2014 T6. We made the assumption that our slenderness ratio, our L over R, is going to be greater than 52.7 or equal to, and we said it was equal to that, so 52.7. So therefore, this is our equation for our allowable stress. We use this over here to the right in units of MPa. So there's that 356 times 10 to the third MPa, all over our slenderness ratio, L over R, quantity squared. So this is where that came from back in our textbook, and this is that equation 10.4a, in our case, part B, because we're dealing with units of MPa. Now, setting those two equations equal to each other for our sigma allowable, our allowable stress, we now have our 356 times 10 to the third MPa all over our L over R squared, which is our slenderness ratio squared. This is equal to our values for P over A. Well, let's go back to our setup page and write down everything we know. This is again why that setup page is great. So, well, I was given my P, my load here of 60 times 10 to the third newtons. I have my value for area. A is equal to pi times c squared. I have my length for this part A of the problem is 0.75 meters. You can see I've converted to meters here. And I know now that my radius relates to my radius of gyration relates to my value of c here, the radius of our cylinder, by c over 2. So c over 2 is equal to my radius of gyration. So I can plug this information in to my above governing equation here, and I now have the 356 times 10 to the third MPa, all divided by, when I plug in for my L of 0.75 meters, over c over 2 quantity squared. This is equal to, I plug in for my p value here, 60 times 10 to the third newtons, all over pi times c squared. Now I can solve this for c, my only unknown. Rearrange, cross multiply here. I end up with 356 times 10 to the third MPa times pi c squared, which is equal to now my 0.75 over c over 2 squared times 60 times 10 to the third newtons. Solve this out for c. We can first solve for c to the fourth right there. When we do that, we find out that our c value, when we do our math, ends up being 0.01864 in units of meters. So pay attention, we're in meters right now, not in millimeters, but we convert back and forth if needed. So now we'll continue on and take a look at our slenderness ratio, that L over R. So we can see our L over R, well, we have a relationship for R and C, so this is going to be equal to our L over C over 2 when we replace our R with that value for C over 2 that we showed earlier. So with this, what do we know? Well, we know for our part A that our L is equal to 0.75 meters or 750 millimeters, and our C is equal to 0.01864 meters or 18.64 millimeters. For this case here, let's leave everything in millimeters. So L over R is going to be equal to our 750 millimeters divided by C over 2, or our 18.64 millimeters divided by 2. Our millimeters will cancel out for our units, so our L over R is going to be equal to, when we do out the math, 80.5. Now this is greater than our 52.7 from our assumed from that problem statement for our slenderness ratio. So that assumption that L over R is greater than 52.7 is correct. So we're all set. So for our length of L is equal to 750 millimeters, the required diameter is simply going to be D is equal to 2 times C, which C is the radius of our rod. So 2 times our 18.64 millimeters, our diameter of the rod is going to be 37.3 millimeters. So now we go back to our setup page and our problem statement and realize there is a part B. We've only solved for part A. Part B was to do the same thing, but now for a value for our length of L is equal to 300 millimeters or 0.3 meters. So we're going to make the same assumption as part A to start off with this. We're going to say that L over R is going to be greater than 52.7. So we'll use our equation 10.48b from our textbook, and we'll follow the same procedure as we did for part A. We'll find that from this here, our C is equal to 11.79 millimeters. Well, let's just go through, double check that, and I'll show you how we step through each step of the way for that. So we find this by starting out with that relationship for allowable stress given to us as 365 times 10 to the third MPa, all divided by our L over R squared. So again, that's coming from that same chart that we saw before. And for our centric load, we still know we have this relationship that our sigma allowable is equal to P over A. So we can set these two equal to each other just like we did in part A of our solution and solve. The difference now is we're going to have a value of L of 300 millimeters rather than 750 millimeters. So we set those two equal to each other, and we have this relationship we see here. We have 356 times 10 to the third MPa, all divided by our slenderness ratio squared, is equal to our P over A. Again, I'll just write out each of those variables, what units we have, what values we have. So P is equal to 60 times 10 to the third newtons. A area is equal to pi times c squared. Length is equal to 0.3 meters, or 300 millimeters. And our r is equal to that relationship of c over 2 for our radius of gyration. Now we can plug in our known values to this above equation up here. And when we do that, we find we have 356 times 10 to the third megapascals divided by this new length here of 0.3 meters, all divided by c over 2, quantity squared, is equal to our p value, which is the same as part A, 60 times 10 to the third newtons, divided by our pi c squared. We can solve this for c. Again, we can cross multiply this, come up with this relationship here, solve it for c, and we find that c is equal to that value we said earlier of 11.79 millimeters. So this is converting this to millimeters here. So based upon that assumption for our slenderness ratio, we now have that diameter for D. We need to check that assumption next. So we go to our slenderness ratio, our L over R, or we're plugging in relative to C. This is L over C over 2, where our L for this case here is going to be equal to 300 millimeters, and our C that we just found is equal to 11.79 millimeters. So we can plug those values into this above equation to check our assumption on that slenderness ratio. So L over R is equal to 300 millimeters divided by 11.79 millimeters for our C value divided by 2. So that value for our slenderness ratio comes out to be 50.9, which is going to be less than that 52.7. So our assumption was that it's supposed to be greater, but it's not. So since this L over R is less than 52.7, this assumption is not correct. This is wrong, and we need to go back now and make a new assumption. So for our new assumption, now let's assume that our slenderness ratio L over R is between 17 and 52.7. So we can use our equation 10.47b for the design of this rod. So let's go back now and take a look at our textbook at this equation. So you can see we're still dealing with the same materials we did in part A, our alloy 214T6 for aluminum. But now, rather than looking at our assumption down here of our slenderness ratio being greater than 52.7, we're going to take a look here and say it's going to be between 17 and 52.7. So therefore, that's where this equation comes from here. Our allowable stress is equal to an MPa, 273.6 minus 3.205 times that ratio L over R plus our 0.0836 times the slenderness ratio squared, again in the units of MPa. So that's where this relationship came from our equation 10.47b in our textbook. We also know that for centric loading, our allowable stress is equal to our P over A. So we can set all of this right here equal to our P over A, where our value for L is 300 millimeters and our value for R is C over 2. We convert this to meters to 0.3 meters, plug into this above equation here for our L and our R, we end up with 273.6 minus 3.205 times now 0.3 meters divided by C over 2 plus 0.00836 times 0.3 meters divided by C over 2 quantity squared, which is going to be times 10 to the 6 pascals rather than megapascals. We convert to pascals here to make sure our unit analysis is correct. This is equal to our right-hand side of the equation, 60 times 10 to the third newtons, all divided by pi times c squared for our area. We plug that in for our rod. And we solve this for C. We find that C is equal to 11.95 millimeters. So now we can go back and do that double check again, look at our slenderness ratio, or L over R, which is in our case here L over C over 2, which is 300 millimeters divided by this value of 11.95 millimeters over 2, which is equal to, when we do all our math here, shows our slenderness ratio is going to be equal to 50.2. So our L over R value is 50.2. So from our second assumption, we assume that our slenderness ratio is going to be between 17 and 52.5. We found it to be 50.2. That means it is between those two values, so therefore our assumption was correct. So for our length of 300 millimeters, the required diameter is going to be that our diameter is equal to 2 times that radius C. So D is equal to 2 times that 11.95. So D is equal to 23.9 millimeters. So now I want to move on to the topic of eccentric load design. We've just went through the beginning of this module dealing with our centric load design. So now we're going to take a look at the design of columns subjected to this eccentric load. So the formulas we used before in the previous sections for columns under the centric load can be modified slightly when using this load P when it's applied a distance away E, which is known as our eccentricity. So we can see now for an eccentric load, there's our load P. Rather than being applied at point C where it'd be a centric load, it's applied a distance E away, so now it's an eccentric load. So back in chapter 4, we saw that an eccentric load, axial load P, applied in plane of symmetry can be replaced by an equivalent system considering the eccentric load P along with a couple M. And we see that M was equal to PE. So that's what we have down here in our diagram. We can see there's our load P centric, and now this couple moment M right here, which is equal to P times E, which is that P times this distance right here that creates a moment, force times the perpendicular distance. We previously went through and shown that we can use that relationship. Where again, that E is going to be the distance from the line of action of the load to the longitudinal axis of the column right there. So that's our distance E. So continuing on with this eccentric load design, we can summarize what we just said in our last slide there, that an eccentric load P may be replaced by a centric load P in a couple moment where M is equal to that P times that distance, eccentricity distance, E. So again, there's our P right there, eccentric load right there. This can be replaced by this load, centric load P, acting at point C here, and this moment that's equal to P times that distance E. Now, normal stresses can be found from superimposing the stresses due to the centric load in the couple, and this is related to our equation 10.53 in our textbook, where we can see our sigma is equal to our sigma centric plus our sigma bending, and we can see that our sigma max from equation 10.54 in our textbook is equal to P over A plus now that moment that we defined above here times C, all divided by our I. So now looking at this relationship from 10.53, where we're saying that our normal stress can be found by superimposing the stresses due to centric load and the couple, we can look at that in terms of a visual graphic down here in our figure in the bottom left. So this shows the normal stress of an eccentric loaded column is the superposition of the centric axle and bending stresses. So this is our centric axle stresses right here, which is our sigma centric, which is equal to our load over area right there. So we can show that on our left-hand side, plus now we have this from our bending right here, which we now have this is our MC over I. So adding these two together is going to give us our normal stresses. So from that here, that's how we come up with our relationship that we see in equation 10.53. Now we can also utilize our allowable stress method for this eccentric load design, and that relates back to our equation 10.55 in our textbook, where we have this relationship that we've seen from 10.54, where we have that stress from our centric loading and our stress from our bending right there added together. This needs to be less than or equal to our allowable stress right there for our criteria for our allowable stress method, again relating to equation 10.55 in our textbook. Now we can also use our interaction method, which relates back to our equation 10.53, where this shows that P over A divided by our allowable stress centric plus MC over I divided by our allowable stress bending must be less than or equal to 1. Now, if we think about where does this come from and how does this relate back to our equation 10.55, well, let's just say we divided both sides by this sigma allowable. So sigma allowable divided by sigma allowable would give us a value of 1. So that's a 1 over there. Then we divide each of these by that sigma allowable, which is exactly what we've done on both sides of this relationship here, where on the left-hand side of this right here, this is for our centric load, and the right-hand side, this is for our bending load. So that's how we come up with our equation 10.57 from a relationship we see here in our equation 10.55 for our allowable stress method.